All right, let's dive in. In this explainer, we're going to become electronics detectives. We're going to learn the secret language of circuits so we can figure out why things break and how to fix them. Let's get to it.
You know the feeling, right? 1 minute, everything's humming along just fine. The next, complete silence. Your dishwasher, your AC, whatever it is, just gives up the ghost. And you're left standing there with a broken machine and no idea why.
But what if I told you that you could find the problem yourself? Because inside every single one of those devices, there's a kind of map. And if you know how to read that map, you can track down the exact part that's causing all the trouble.
So every investigation has to start somewhere. For us, it's with the blueprint of the crime scene. Before we can find any culprits, we've got to understand the layout. And for that, we need a very specific kind of map.
Now, you're going to run into two types of these maps out there. On one hand, you've got a wiring diagram. Think of that like IKEA instructions. It shows you where the physical parts go. But what we're after, our real treasure map, is the schematic. A schematic doesn't care about the physical layout. It shows you the logical flow, how the electricity actually thinks and moves through the circuit. That's how we read its mind. Okay, so we've got our map, the schematic. But, well, it's written in a kind of code, a language made of symbols. So to be a good detective, we have to learn the language. Let's start decoding some of the most common clues you're going to find.
First up, the most basic component of all, the resistor. You'll see it as this little zigzag line. And its name kind of gives it away, right? Its whole job is to resist or control the flow of electricity. It's basically the traffic cop of the circuit.
Next up is the capacitor. You can think of it like a tiny, super fast charging battery. It stores up a little bit of electrical energy and then releases it. Now that curved line on the symbol, that's a huge clue. It means the capacitor is polarized. You have to put it in the right way, positive to positive, negative to negative, or it's just not going to work. And this guy? This is a diode. It's basically the bouncer for the circuit's nightclub. Electricity is allowed to flow in one direction, the way the arrow is pointing, but it is not allowed to go back the other way. It's a one-way street, pure and simple. Of course, there's a whole crew of other components you'll see. And on a schematic, each one gets a label like R1 or C3 or Q1. This table just shows you some of the most common letter prefixes you'll see. S for a switch, Q for a transistor, and U for the real brains of the operation, the integrated circuits or chips. Think of these as our cast of characters. Okay, so we know our suspects and we can read the symbols on the map. Now it's time to learn how to actually follow the trail of electricity from one place to another. All those lines connecting the symbols, we call those nets. They're the wires. Now here's a key detail. Where two lines cross, look for a dot. That dot is called a node, and it means those wires are electrically connected. If you see two lines cross with no dot, they're just crossing over. They aren't connected at all. All right, quick timeout, because this next part trips up a lot of people. You might have heard in a science class that electrons, the things that make up electricity, actually flow from the negative side of a battery to the positive. And that's true. But for our detective work, we use something called conventional current. It's just the standard way everyone agrees to draw schematics. And in that world, we say current flows from positive to negative. So just for now, forget the electrons and follow the flow from plus to minus. It makes everything way easier. So, we know which way the current's flowing, we know what the symbols mean, and we know how to read the map. It's time to put it all together. Let's apply this to a real-world mystery and actually crack the case. When something's broken, it is so tempting to just start poking around randomly. But you can't do that. A good detective is methodical. You have to have a system. If you don't, you'll miss clues, or even worse, you'll end up replacing a part that was perfectly fine to begin with. And a fantastic system to use is called the Hopscotch Method. It is so simple. You just follow the path of the current with your multimeter. You start at the beginning, and you hop from one component to the next, taking a voltage reading each time. You keep hopping until suddenly your voltage reading drops to 0. The component right before that drop, that's your prime suspect. Let's put this into practice. Here's our case file. A customer's HVAC unit is on the fritz. The big compressor unit outside is running, so we know the system has power. But inside, the fan that's supposed to be blowing the cold air, it's completely dead. So we pull up our schematic and we can immediately line up the usual suspects. If we trace the path of electricity to that fan motor, we see there are a few things that could be stopping it. Maybe the switch in the thermostat, maybe something called a relay, maybe a capacitor, or, of course, the motor itself could be bad.
Time to start hopscotching. We've already confirmed the thermostat is sending the signal, so our first real stop on the schematic is the indoor fan relay. A relay is just an electrically operated switch. We're going to use our multimeter to see if voltage is making it past the relay.
And there we go. The meter reads 240 volts. That's exactly what it should be. This tells us the relay is doing its job. The switch is closing. So the relay is not our culprit. We can cross it off the list and move to the next suspect in line. Our next hop takes us to the run capacitor. This little guy's job is to give the motor a bit of an electrical kick to get started and keep it running smoothly. The schematic tells us it's supposed to be rated for 5 microfarads. Let's check it. The meter reads 4.9 microfarads. Now, capacitors have what's called a tolerance. Usually it's about 10%. Since 4.9 is well within that range for a 5 microfarad capacitor, we know this component is healthy. Well, we've cleared the relay, we've cleared the capacitor, and that leaves only one possibility left on our list.
By following that trail of clues, we've identified our faulty part, the motor. But, a truly great detective doesn't just stop there. Finding the broken component isn't the end of the story.
Let me put it this way. Say you find a blown fuse, you pop a new one in, and the machine turns back on. Case closed, right? No way. All you did was fix the symptom, not the disease. And that's the real goal here. A fuse doesn't just blow for fun. A motor doesn't just fail for no reason. You have to ask why. Was the motor drawing way too much current, causing that fuse to blow as a safety measure? Was a bad bearing in the motor making it work too hard until it burned out? Every failed part is a clue to a much bigger story. And now, with the ability to read a schematic, you have the key. You can finally read that story and find the real root cause.